then let's hand over to Philipp Kindermann, our first speaker. So while the slides are switched, Philipp is a professor at the University of Trier, and I think from his PhD days or maybe master thesis days working in graph drawing, he did his PhD in Würzburg and is in Trier for a couple of years now. I guess most of you know Philipp anyhow. So with this, I would just hand over to Philipp for the first lecture. Thank you.
Does this work? Okay, thank you for the invitation. It's nice that so many people showed up. So when Martin and Robert invited me, I was thinking, of course, okay, what should I tell you? And then I saw the list of speakers, and I saw there are many topics. And then I decided, okay, one of us should do some classic graph drawing stuff. So I was switching between a few topics, and in the end, by discussing with Martin, I decided, okay, when I was a PhD student, I was working on some paper in Perugia, visiting them, and suddenly they said, okay, now we've done this, we can do this with SPQR-Trees for bi-connected graphs. And I was sitting there, what? And then they were talking, okay, we do this, and then we have these nodes and whatever, and I could not follow at all. So I thought, well, it would have been nice if I would have known what SPQR-Trees are and how they work. So for you not to fall into the same trap as me, I will try to give you some introduction. What is this, and how do we use that? So just that we are on the same page, very brief stuff, you all know this. Planar graph is one we can draw without crossings. And of course, there are many different ways to draw them. And some of them are the same or similar. And those drawings that are similar, that we call those that have the same combinatorial embedding. And there are two ways to define that. The first one is that we look at the faces. So the faces are just the connected regions of the plane that are bounded by the edges or vertices. And if we look at these two drawings, and we color the faces, then we see that for all these colors, we have the same vertices in order around them. So these two have the same combinatorial embedding. There's an outer face, there's some inner faces, and there's the first thing where it may be different, because sometimes when we talk about same combinatorial embedding, we mean with the outer face. Sometimes we don't care what the outer face is. Usually the combinatorial embedding doesn't care. And if you also want to say they have the same outer face, then you have to specify that. And so for us, combinatorial embedding is just the description of the faces. Or equivalently, we can look at every vertex and then look at all the edges around it, and then we get a circular order of the neighbors. And then that also describes the embedding to us. And these are completely equivalent when the graph is planar. When it's not planar, then they are not equivalent. And it's also only equivalent when the graph is connected. Otherwise, we also have to describe for the connected components how they lie to each other. So this is what we talk about when we say we want a combinatorial embedding. And when we have a planar graph, like I said, we have many different ways to draw it. And the SPQR-Trees, they are a tool that we can use to look at all different embeddings. There might be exponentially many, so we cannot save all of them. So we want a data structure that is small, where we can still kind of look at all different embeddings or all ways that we can change the embedding. And the way we use this is that usually we look at some problems, and of course we try to simplify it first, and once we solve the simplified version, we try to extend it. So in order to do that, we of course need some problem. So I'll give you a very simple problem. You have a planar graph, and now you have two vertices, Mario and Peach, and you want to connect them via an edge. And of course you would like to do this in a planar way, but sometimes it's not possible, like here. Whatever we do, we need crossings, so we want to do this in a way that we have a minimum number of crossings. In this example, it was very easy. We did it with two crossings is optimal, but there are examples where we can see that it's maybe not that easy. If we look at this graph, this is basically just a double wheel, but here everything on the cycle we've subdivided by many, many parallel paths. And now if I place Mario and Peach here, and I use this drawing of the graph and I try to connect them, then we need k crossings, depending on how many parallel paths we have. But of course, probably most of you can see there's a better drawing. If we take Mario and we flip him inside here, then we only need 4 crossings. So this can be done much better. And in fact, it has been found out by Cabello and Mohar that this problem is already NP-hard. So we have a planar graph, we add 1 edge, we want to minimize crossings, it's NP-hard. So that's tough for us, but then of course it's not the end of the world. We will just make the problem simpler. And we say, wait, I start with a planar graph. Why should I draw this in a way that it's not planar? I want to keep a planar drawing. So we adjust the problem. We say the input graph still has to be drawn planar. And then this does not work, because here we have crossings between black edges. This is not allowed. And now actually this is the optimal drawing, or one of the optimal drawings. And if we add this restriction, then we can solve the problem in linear time for any planar graph. And this is basically the algorithm that I want to show you with a few adjustments. And we want to go through the whole pipeline. How can we try to solve this for any planar graph? And the standard pipeline is we look at a very specific graph class first that we can solve, and then we try to extend this graph class. And we try to extend it as far as we can until we hit a wall. And usually what you do is you start with something very simple like a triangulation, or maybe a 4-connected triangulation, if you cannot do that. If you're brave, you can start with a 3-connected graph. So the first step would be we try to solve this problem for any planar graph that is 3-connected. If we've done that, then we try to solve it for biconnected graphs. If we've done that, then we try to solve it for connected graphs. And if we've done that, then we try to solve it for disconnected graphs. And there's some standard tools that we can use for that. The disconnected graph is usually pretty straightforward. If you can do the connected, then disconnected is usually not much harder. But if we want to go from the true connected to the connected case, then we usually use a data structure that calls block cut trees or BC trees. Probably most of you have seen that at some point. And if we want to go from 3-connected to the 2-connected case, then we need the SPQR-tree data structure. OK, so let's try to do that. We will not follow from top to bottom, but we will start with the easy case, and then we go bottom to top so that we can save the most interesting for the last. So let's start with the 3-connected case. Now, let's say we have some 3-connected graph. We have Mario and Peach. And now you can think for a second, what is the nice thing about a 3-connected graph that we can abuse that makes the problem so easy? Who has an idea? Yeah, this very important theorem by Whitney, 90 years old. Every 3-connected planar graph has a unique combinatorial planar embedding. This theorem is a bit stronger. It even says it has a unique combinatorial embedding if and only if the graph is a subdivision of a 3-connected planar graph. That we don't need. This simpler version is enough for us. So what we want to do is that we want to first create the dual of the graph. The dual means we take every face and we place a dual vertex there. So we take this triangle, place a vertex here, take the next one, place a vertex there, and then we connect the dual vertices if and only if there is an edge between the faces. So we continue, we draw all the face vertices and all the edges in between until we get the dual of the whole drawing, and of course, in the end, also one on the outer face. Let's move this away a bit to the side. That one we usually denote by G star. That's the dual of the graph. And now we want to work with the dual. But the dual alone is not enough because we don't have Mario and Peach anymore. So we have to augment the dual. We take Mario and put it wherever it's supposed to be, here. We take Peach, put it there. and we add some connections to the faces that are incident. So Mario lies on this, and this face, so we add these 4 edges. And the same here at the bottom. And now we want to find a path from Mario to Peach that gives us the minimum number of crossings. And for that, we can use the dual. We just start with Mario. We look at some path. The shortest is probably very good. And we follow it to Peach. And now we can use this path here in the primal to draw our edge. So the path starts with Mario. It goes to this face, so we go here. Then it goes to this face, we go here. It goes to this face, we go here. And then to Peach, and then we have it. And the nice thing is, if we count the number of crossings we now have on this path, that's just the length of this path here minus 2. Because whenever we go from a face vertex to another one, we are crossing an edge. That's just what we have here. Every edge becomes an edge. If we go from a face to a face, we have to cross an edge here. So finding the shortest path in the dual means that we have a minimum crossing edge in the primal. And of course, that's not a unique solution. There are many different ways. I found 4 ways to route this edge. Maybe there's even more, but that's fine. So this is the solution if we have a 3-connected planar graph. It's actually even a bit stronger because we don't really use the fact that the graph is 3-connected, except that we have a unique embedding. This algorithm works whenever we have a graph and we don't want to change the embedding at all. The thing is just that with 3-connected graphs, we cannot change it, so whatever. So we have our first lemma. We can solve this problem for 3-connected graphs, and everything we've done here works in linear time. You have to be a bit careful with data structures, but we don't care too much about that today. So you can believe me, this is a linear time algorithm. So we've done the very first step. We've solved this problem for 3-connected graphs. And as I said, we now want to come from the bottom to the top. So let's start with a disconnected case. Now we want to have a look, how can we reduce connectivity requirements? So let's assume we've already done this. We know how to solve the connected case. How can we use this to solve the disconnected case? Like I wrote, it's usually straightforward. It is the same here. So just assume we have a few connected components. And we just have to look at 2 different cases. The first is Mario and Peach are in the same castle, like this. You can think for 5 seconds, that should be enough to solve this. We ignore all other castles. Now we have a connected graph, and we solve it. We're done. The second is the princess is in another castle, like this. Again, I'll give you 5 seconds to solve this. Should be enough. You ignore all other castles. And now we embed both castles in a way that Mario and Peach are on the outer face. So we change the embedding here. And now we can connect them without any crossing. And we're done. We have solved the disconnected case, assuming that we know how to solve the connected one. That's the first connectivity requirement that we reduced, from connected to disconnected. And of course, also the easiest. So let's get to the more interesting one. Assume we know how to do the bi-connected case. How can we extend this so that we can solve the connected one? And for that, we want to use the block cut trees. So first, we have to have a look at the data structure. A block cut tree, there are, of course, many, many different definitions. I give you just my favorite one. This is a tree that consists of 2 types of nodes. We have C nodes. These are cut vertices of the graph. And we have B nodes that are blocks of the graph. And a block is a maximal bi-connected subgraph. We are a bit cheating here because we also look at edges as maximal bi-connected subgraphs. We're technically in edges, probably not bi-connected, but we have to cheat a little bit to make the definitions easier. And in the BC tree, we have edges between these types of nodes that just tell us which cut vertex lies in which B node. So let's just have a look at one example. This is our connected graph. We want to find a cut vertex. One cut vertex is here at the top, so let's mark it. If you remove this vertex, then the graph becomes disconnected. That's why it's a cut vertex. So we need a C node in the BC tree that contains exactly this cut vertex. Let's try to find another one. There's another one here. If you remove that, it gets disconnected. So we have another C node. And now that's where the cheating part comes. So there's an edge between them. So we want one block that consists exactly of this edge, and that's connected to the two C nodes, and that we have here. So this is our edge. There's another connected component that contains, or another block that contains this cut vertex, which is this one here. So we make another B node for that and put it here. And now we do the same. We walk through the whole graph. We find another cut vertex. There's a block between them. So we put it here. We find another cut vertex here. This one's a bit special because here the block looks like this. There's a hole in it. That can also happen. So we have component. We have another cut vertex. And here we have another component that's just one edge. And that way we get the whole block cut tree. Yeah? Essentially only cut edges, yes, except this. So,
which is a cut edge because it is disconnected.
Yes, yes. So all the blocks are either maximal biconnected subgraphs or they are bridges. So an edge, if you remove it, then you get two or more. Well, it has to be exactly two connected components. Well, that's the cheating part here, so the definition. Other questions so far? Okay, this is the data structure that we want to use. There are some nice properties. So for example, if I look at a C node, then all its neighbors of course, have to be B nodes, and they all have to contain the cut vertex, and it's nowhere else. That's very nice property. So all the nodes that contain some cut vertex build a star, and all the nodes that contain some vertex that's not a cut vertex, like this one, that's just a single B node. And we want to use this now. So let's have a look at the algorithm for the connected case. We assume we can solve the biconnected case, and we start with building the BC tree. Now, of course, we need Mario and Peach. So let's place them somewhere. They are here. And to use the BC tree, we have to find them. So Mario is here. That means he lies in this component. And Peach is here. That means she's this cut vertex. So Mario appears in exactly one, and Peach appears in multiple nodes. We need to find an edge from Mario to Peach. So we want to find a path in the dual. That means that we somehow have to walk through all these components on the way. So we first want to find the path between Mario and Peach in the BC tree. This is, again, not a very technical definition because there's not a path between Mario and Peach because there are many nodes that have Peach. But it's not so hard to see that there's exactly one shortest path between them, because all the nodes that contain Peach build a star, all the nodes that contain Mario build a star, and we are in a tree, so there's always a unique path. So whenever we have a longer one, like here one, we can just shortcut it and we stop at the first time we appear at Peach. So we have a unique path here. And this path we want to use, and we want to walk along it and build our edge. And on this path, we have all these different maximal biconnected components, or edges, and we assume that we know how to solve them. So let's start with exactly that. We look at all those B nodes on the path, and we use our algorithm that we already have to solve it. Okay, we ignore the rest, And now we place our paths here. So here we want to go from Mario to the other cut vertex. Here we stop working. Okay. We want to move between the two cut vertices. So we find an edge here. We want to go from one cut vertex to the other, one cut vertex to the other, and finally from the last cut vertex to Peach. So we always want to start either with Mario or Peach, or we have to go to the cut vertex, and the cut vertices between which we want to walk are just those that we have here on path. So we insert all these edges. And now we want to combine this. So let's just do it the easy way. We just insert the edges the way we've drawn them. So we insert an edge from Mario to the purple. We go backwards, we go from peach to red. Then we go from red to green. Then from green to pink. From pink to purple. And from purple to Mario. And we have a path. Thing is, it has a problem. It's a path between vertices. Of course, we won't just add a single edge. So that's not allowed. So we have to do something more. We want to route around the vertices that we have in between. So when we arrive here, we don't go to the vertex and leave, but we just go slightly around it. And then we get this path. And now if we add this edge this way, then we do it with 3 crossings. That's great, right? No? What's the problem? There's one with 1 crossing, yes. Can we even do less than 1? Yes. Okay, so it's very clearly not optimal. So if we draw our edge like this, then we have 1 crossing. And we can also flip this one here outside, and then we could connect it without any crossing. And it's pretty obvious because so far we've not really done a lot. We've just added a few edges and then tried to combine them. Of course, this cannot work. So we have to adjust the embedding a bit. That's the important part now. And there are 2 things we have to do. The first thing is this crossing here is completely unnecessary. So I go through this edge. I could also just go around here. So we don't want to have these kinds of crossings. There are 2 ways to do this. Either we find a different routing, we go this way, or that's a bit tough to define how to do that. So instead, we just change the embedding. So we look at every cut vertex on the path. And for every C node, we want to embed all the blocks around it such that there's nothing between these 2 green edges. So in this case, this would mean we want to embed this in a way such that we go here, and then we can go here without any crossing in between. And we can do that by just flipping this whole thing, and then we get this. And we got rid of 1 crossing. Let's look at the next, the green. We come from here. We want to go through there. That's not great. If we look around this green vertex, we have black, green, black, green. We only want 2 green that are consecutive. So again, let's flip it. Move this here. We move this component there. And we got rid of 1 crossing. Now let's look at this C component. If we look around it, we have black, black, green, black, green. So we try to re-embed it, but now we have a problem. Whatever we do, if we flip it, we cannot get the 2 greens together. So we have to do even more. Now we also have to look at the B nodes. So we want to change the embedding of this whole block here. What should we do? Any suggestions? It's still connected, yes. We've already kind of fixed our embedding using the 2 connected case, but there's one thing we can still do to make it better. Yes, we can still pick the outer face. And that's the important part. So we know we arrive here with our green edge from the outside. And now we do a crossing so that we can continue with the greenish. That's not something we want. So we want, when we connect there, that the connection is on the outer face. So we re-embed this such that the last part of this green edge, which is where it connects to this cut vertex, lies on the outside. So we move this, and we get this embedding. It's the same combinatorial embedding, but we chose a different outer face. And if we do that here, then it's looked like that. And now we finally have an embedding where we can insert this edge without any crossings, and we even have found the way to insert this edge. So that means we have also solved the connected case, assuming that we know how to solve the biconnected one. The clock in the back is tricking me because it's stuck. But it's almost correct. Okay. Any questions so far? No, it might be that we need crossings. No. If they're sitting in different, I mean, there can be a lot of stuff around it. It's only the last part of the segment. It might be when we use the algorithm for the biconnected case that this already requires crossings. So we can only make sure that the last part is here. Might be that there's a lot of more stuff and the cut vertex lies inside here, and then we have to go through. This is just a nice example where it works out somehow. Okay, so this is our first data structure, the block cut tree, that tells us how we can walk through the biconnected components and then combine stuff so we can solve the connected case. And of course, there's a reason why I've done it this way around and not from top to bottom, because now we're at not even the half point and we still have the last part left. And understanding the block cut tree, how we construct it, also helps us to understand how we can construct the SPQR-tree. Well, the thing you want to keep in mind, what we've done here is we were looking for cut vertices, and we split the graph along these cut vertices into smaller components that have a larger connectivity. That's always the strategy. If you want to reduce connectivity requirements, then you have to find smaller chunks that have larger connectivity and figure out how you have to glue them together to get the large graph. That's the same as we want to do in the next step, which is the final thing we need to solve the whole thing. We have something at the top, we have a lot at the bottom. We need this one here so that we can solve the whole problem. And for that, we need SPQR-trees. And for SPQR-trees, Nico Fink is not here, but he told me that there are about 5 different definitions that are all equivalent. I will only show you 2. They all have their advantages and disadvantages. The 2 I will show you are the ones that are most useful for algorithms. They are not so great to prove properties about SPQR-trees. They are not so great to prove that it's unique. But today we only want to use SPQR-trees, so this is enough for us. And we want to look at 2 definitions. One is by decomposing the graph, and one is in the other direction by composing the graph. And the first one, the decomposition, is the one that's the closest to the BC tree. In the block cut tree, we were looking at cut vertices, and we split the graph along these cut vertices into smaller components. Now we assume the graph is biconnected, so of course there is no cut vertex, but there are cutting pairs or split pairs. So since it's biconnected but not 3 connected, it means that there are at least 2 vertices. If we remove these 2 vertices, then the graph becomes disconnected. And these are the split pairs that we want to find. And again, we have to be a bit cheating. We also have to use edges here as smaller components. So a split pair tells us either the two vertices are connected, or if we remove the two vertices, then the graph becomes disconnected. So any edge gives us a split pair if we also look at edges in between. But also, if we look at these two vertices, then they are a split pair by both types of definitions. There's an edge between them, but also, if I remove them, then it splits the graph into more disconnected components. So what we want to do is, we want to start with some edge, let's say this one here, and this builds the root of our SPQR tree. And then from there, we want to walk downwards. So this is where we start, this edge, and now we find split pairs. This conveniently is one, so we split the graph between them. We get this edge, we get a connected component here, we get a connected component here, connected component here, and a connected component here. And as you can see, I also added some dashed edges here. These are not real edges, but this is now the first difference that we have to do. We always have to add a fake edge to every component that we get from the splitting, such that it remains bi-connected. Otherwise, it could be that we split among something and then we get a simply connected thing that we don't want. We always want that every component is at least bi-connected. And on the side, we build our SPQR tree. And that tree is supposed to capture what we've done. So what we've done here is we have one edge. This is here. And we have these two vertices. So these two. And if I remove them, I get 4 components. 1, 2, 3, 4. Those are here. 1, 2, 3, 4. That's my components. That's how we want to show what lies here. And each of them now gives us a different subtree, and we want to keep on decomposing. So let's have a look at this component here. This is again bi-connected because we added this fake edge. And we want to find more split pairs here. So we can start with the top edge and split among that. We can also take these two vertices and split there. We can take these two vertices, split there, and then we remain with one edge. So we found a bunch of split pairs, and if we decompose this way, then we get something like that. We have an edge, then we have a component, and we have another edge. And again, everywhere we have to add this fake edge around. And that fake edge that basically tells us if I want to put everything together in the end, that's where the other stuff has to go. Let's continue. This is an edge. We don't have to do anything here. This component here. We want to look for another split pair. But if you stare at it, you will see this graph is already 3 connected. There's no split pair inside here. So we just keep the whole component. We put a 3 connected component here. There's no split pair we can use. If we look at this one, then we see, okay, the top and the bottom vertex. If we move them, we split it. So we get something that looks like this. 2 components that are parallel, and the fake edge. And if we look at these two, then we can again split in the middle, put 2 different edges. We get 2 edges here, 2 edges here, have smaller components. So this part is done. Let's take the next one. Again, find split pairs. We want to find something that we can split into. So these two, for example, work. And then also these two work. So we can do a split like that. And then we recursively go into the components. Here, we cannot do anything. Here, we also cannot do anything. So we keep those. Take the next one. We have split pair here and here. So we can get 2 components. An edge is done. Here, we can again split with the top and the bottom. We get two different components. Here we get two edges that we can split in the middle. Here we have something where we cannot do anything. And here we have an edge. And the final component, we can split between here, between here, between here. So we get this. Here we can still split into two parallel parts. And there we have two edges that we can split. And then we're done. And now this is the SPQR tree that we get from this input graph by decomposition. Of course, there are now many questions. What have we done here? Somehow, I just arbitrarily picked some vertices and said, yeah, we can split here. Yeah, we can split here. And we can do that. But we have probably, if you haven't seen SPQR trees, you have no clue how did I decide how to split. Sometimes I took edges. Sometimes I took components. Sometimes I split it like this. Sometimes like this. It all looked very arbitrary. But there are some rules. Which is the nice thing. So let's have a look at those rules. But first, you can also see that I somehow colored all these components. And just by staring at it, you probably see some structure. Why I colored some components in the same color. So if we look at all these blue components, then that's always a vertex at the top, at the bottom, and some components or edges in between. If we look at the red components, then it's always, we have some components that are stacked on top of each other. And if we look at the green ones, then that's always, yeah, it's reconnected, there is no splitting pair here. And that's the different types of nodes that we get from different rules. So let's have a look at these rules. If we want to do the decomposition, we always have to start with some split pair. Usually, you also want them to be connected, so we start with some edge. And we use structure considerations of the graph to further split it. We always have everything with regards to these two vertices, S and T. These are also what we call the poles. And we get 4 different types of nodes. The first one is the Q node. So this is now where SPQR comes in. We have 4 different types of nodes, S, P, Q, and R. Q is just a single edge. And technically, if you build the SPQR tree, for every edge you have one Q node that contains only the edge. But usually when you draw the SPQR tree, you just forget about it and you leave the edges wherever they are, because everything will get too large and cluttered. And they're usually trivial anyway. So let's not consider them too much. First case, we have our top vertex and our bottom vertex. And that's the first type of split I did. I walked from top to bottom. And on the way, I found a bunch of split vertices. So we want to separate S and T by a bunch of cut vertices that are on the way. And that gives us an S node that looks like this. If I walk from S to T and I forget about the fake edge, then there are a few cut vertices in between. If we can do that, then we do that and get our child components this way. And the child components are now the subtrees that we get from these here. So we want to decompose the components that we get between the cut vertices further to get the rest of the SPQR tree. That's the first rule. The second rule, if I cannot do that, then I cannot cut like this, so I try to cut parallel, like that. If I can remove the two vertices, the two poles, and the graph gets disconnected, then this is a parallel decomposition. So if I remove S and T, and I get several components, then it looks like this. And each of these components that we get, that again becomes a smaller node that we want to further decompose. And the final thing is, if I can do neither, I cannot find cut vertices here on the path. the graph still stays connected if I remove S and T. Then it's the final node, which is the R node. And that is basically 3 connected. There's one thing I didn't tell you. These don't have to be 3 connected. There can be stuff in between here, in between here, in between here that you further want to decompose. And that's the weakness of this, because finding them is, you have to somehow find maximal split pairs in between to further decompose, and this is really ugly, so that's not something we want to formally define. But this is the first way that we can create the SPQR tree by decomposition. And the nice thing is that if you write down all these rules, then it immediately gives you an algorithm, with this last part being a bit ugly. But we can use all these rules. We can build the SPQR tree. So this is a constructive way to build the SPQR tree of a graph. It shows us that there is always some SPQR tree. We can compute it fast. But the weaknesses are, of course, it's not really clear that the SPQR tree is unique, and it's really hard to prove stuff. So for using it for algorithms that we want to utilize the SPQR tree, it's not so great. But the great thing is that Mutze and Gutwinger used exactly this decomposition to prove that we can compute an SPQR tree in linear time, and that also only has linear size, which are some important properties that we need when we want to use the SPQR tree. In a second, we will have a second definition where things hopefully come together. So if we combine these 2 ways to look at it, then I hope everything makes sense. To first have a look at some notation. So if we have one component here, one block in the SPQR tree, we call this a component, then there's always some graph inside. That's called the skeleton. And technically, the skeleton is just a simple graph, so this here is just an edge. We just draw it this way to denote that there is still some component inside here. There are some virtual edges. Virtual edges are one where there's still a component hanging in there that we want to replace the virtual edge with. And there are some real edges. Those are technically just Q nodes that we omit. And there's always the reference edge, that's the fake edge, that tells us where's the rest of the drawing, the rest of the graph. And important are the poles, S and T, that's in the beginning. We choose that, and whenever we decompose into something smaller, that gives us where the poles are. And we have to always apply the rules along these poles. So here we have a series decomposition. If I walk from S to T, then I can find 1, 2, 3 cut vertices. So that's the way we have to split here. And then there's one more definition that we don't use, but that we will read a lot when you look at papers with SPQR trees. That's the pertinent graph. Usually it's not very well explained what the pertinent graph is, but there's an intuitive way. If you look at the SPQR tree, and you look at a single node, and then look at the subgraph of the SPQR tree that's rooted in this node, then that gives you a subgraph of the whole graph. And that's what usually people mean when they talk about the pertinent graph. So if we go back to the composition, this was the right part here. So this is just this whole component. So the pertinent graph of this is this part. Yeah. S and P. What is always connected with net? So you usually want, yeah. So they don't have to be, but the thing is the SPQR tree, there's a rooted and unrooted version. And in the rooted version, you want to start with some node. And usually you want to start with an edge. So your root is just a Q node, and then you start from there. And if you have that, then it's always connected. But in between, if you go further down, they don't have to be connected. It can be just a virtual edge. So,
In that example that
yeah.
drawn here, if I would just omit the leftmost edge,
Yep.
then the two vertices would still be a split pair, right?
Yes.
But they would not be directly connected with an edge. That would
Yes.
still work the same way.
That would still work, yes. Usually you would then start with some other edge. Maybe you start with this edge and go from there.
So is there,
But you can start with any split pair.
is there in a two connected but not three connected graph always an edge, a split pair that is connected with an edge?
Always a split there. I mean, every edge gives you a split pair, so by definition, there's many split pairs that are connected by an edge. So when you start building your SPQR tree, you pick any edge, and that's the root. That's the first split pair that you use. This can be this edge that we used here. It can also be this. It can be any in between. In the end, if you draw this edge will be on the outer face. And then you start splitting from there.
Okay, so the first split pair doesn't have to split the graph.
No, it doesn't have to. Yeah, that's the weird definition of split pairs.
Pair that actually disconnects the graph.
Yes. Yeah, it just has to be one according to this definition of split pair. Okay, other questions? Yeah. So there's, series parallel graphs. There's a way to decompose them. There's the series and the parallel decomposition, S and P. And then for the edges, you just take the next letter Q, and then you have an SPQ tree. And then when the Romans came up with the next, with the SPQR-Trees, there's also the rigid component, so of course you need an R, but probably they chose the word rigid to make it SPQR. But maybe you can ask Pino on Wednesday what he has to tell you about the story of SPQR. He probably knows better. But technically, these are just the kinds of decompositions. S is series, P is parallel, R is rigid, and Q is, we needed one more letter. And that's also the way we want to look at it in the next definition, the definition by composition. So what we've done first is we take the graph, we find some split pairs according to some definition, we split it into smaller parts. Now we want to go the other direction. We start with small stuff and we want to glue it together in some ways. That's very similar to our series parallel trees, graphs. And for that, we define ST graphs. So ST graph is just we have some vertices S and T, and an edge between the two vertices is an ST graph. That's the simplest one. And if we have several ST graphs, then we can glue them together to a larger ST graph by three types of compositions: the series, the parallel, and the rigid composition. The series composition looks like this. We have three different components, for example. It can be 5 or 10 or however many. And we want to glue them together at their poles, but in a series way. So we start with the first component, and we identify the target with the source of the next one. So we glue them together in this way. And then here, we identify the target with the source of the next one. And if there are more components, we keep doing like that. We put them on top of each other. That's exactly the same as what you do in a series composition in the series parallel graphs. The second is the parallel composition. That's also exactly the same as in series parallel graphs. We have different components. We want to glue them together. But now we don't put target to source and target to source, but we put all the sources together and all the targets together. So we start with the first one, and we put the next one there, and the next one, and so on. And then we get a parallel decomposition. And that's also where the name comes from. Here we do a series of different components. Here we put many components in parallel. And if we stop here, then we have series parallel graphs. That's exactly the same definition. But we want to do all biconnected graphs, so we need the last one, and that's the rigid composition. And that's the largest box. And here the definition is a bit tougher, and that's why we needed all these definitions. We want to have some skeleton. So we want to have some graph that's 3 connected if we add the edge ST. So something like this. We take any 3 connected graph with the edge ST, and this builds our skeleton. And now the skeleton means that we want to replace each of these edges. Either we keep it as an edge, or we replace it with some component. So if we have many ST graphs, we can glue them together by taking any 3 connected graph as a skeleton, taking any of these ST graphs, and replace edges here in the skeleton by these components. So we take this, and I already colored in the way I want to replace it. Between S and V, I want to plug in this component. So this here. Between S and U, I want to plug in the pink component. This comes here. Between U and V, I want to plug in the red component. This comes here. And then here, the blue and the orange one. And I replaced every edge with some ST graph, and then just need the final ST edge around it. And to get our nodes in the SPQR tree, no, we just add this fake edge from S to T everywhere, so that the whole thing is at least biconnected, and that we have the reference edge that tells us where is the rest of the graph. So let's try to, or first, do you have questions before we apply this? Let's try to build the graph that we had using these compositions. So we start with just one edge or 2 edges. We glue them together. And now we can do a parallel composition. We put another edge here. Now we can add edges to the top and to the bottom with another series composition. Then we get this component. Then we can do another series composition between 2 edges. We get this component. We have now 2 ST graphs. We can add another one with a rigid component. We get another ST graph from here to here. And we can now use a parallel composition on these different ST graphs. We glue these 2 together. We add 2 edges at the top and bottom, or 1 at the top. Then we add another rigid component. We have another rigid component. We do a series composition to glue them together. So here the target and source become identified. We add 2 more paths of length 2 with a series composition, and we glue them together at the poles with a parallel composition, at this. We add another rigid component. We glue these 2 together. We glue another edge at the bottom, at the top. And in the end, we want to glue all these 4 together at the poles, and we get the input graph. Now that's the other way that we can construct the SPQR tree, starting just from all the single edges that we have in the graph and gluing them together in these 3 different ways, either parallel or serial or rigid with these rigid skeletons. And for me, this definition makes it much easier to understand how we get this SPQR tree and how these different types of nodes are defined. And the nice thing is that all these definitions are equivalent, and the SPQR tree is unique. So if you do the decomposition or you do the composition, you will get exactly the same SPQR tree, except maybe different roots. So it can be rooted in a different edge, depending on how you choose it. But everything here is the same. No matter which way you do it, you will get exactly this SPQR tree. And the nice thing is here, we can much better understand what everything does. But of course, there's also some weaknesses to this. So the thing is, if I give you this graph and now tell you, give me the SPQR tree, it's not so easy to see how do we start, how do we glue things together that we get this. So this is not something that we can use so well to create the SPQR tree of some given graph. That's what we use the other definition for. But these compositions, they are very good if we want to use the SPQR tree with some kind of dynamic program. Because now we know exactly what's going on here. If we look at a node and we see the children, we know exactly how we have to glue these children together to get the larger graph and to solve it for that larger one, if we've already solved it for the children. If you can find some, it's I mean, just looking at the graph, I don't know of an algorithm that does it this way. I mean, the algorithm is that you do the decomposition and you do it backwards. That's the best I know. But figuring out from the sum graph, how do you go from bottom to top, I don't know if there's a good way to do that. Yeah. Yes.
You said before that they could have non-rigid stuff inside.
Yes.
When you do this bottom up, do you just start as like having all the edges? How do you determine when you are rigid or not rigid?
That is the tough part. That is the tough part. So determining this is really tough. So creating the SPQR tree in the bottom-up way is hard. I don't know how to do it. So if I would create the SPQR tree, I would always do it top-down. But if I use the SPQR tree, I would use this definition that I look at a node and I just imagine it has been built bottom-up, so I know how to glue things together.
In a more general SPQR,
yeah.
There could be a rigid node that is not a leaf?
Yes. So we can replace this edge here, for example, with some larger component and put it inside here. Yes, maybe I should have added one at least. So we have these different types of composition. We have single edge. We can combine them with series, parallel, or rigid. And that gives us the names S, P, and R. Like I said, Q is the edge. And this is great for inductive proofs and dynamic programming algorithms. Like I said, it's not so great for computing it. But there's also some other stuff. So if all rigid compositions are planar, then also the composed graph will be planar. And the compositions work with drawings and with embedding. So if we fix the embedding for every skeleton that we have here, and we glue them together, then we get an embedding of the whole graph. And then there's two ways that we can use this that we will now next do for the problem we have at hand. How can we create these embeddings? And yeah, like I said, how to compute it this way is not so clear. So for that, I would use the decomposition structure. One more thing. All the definitions we had so far, they only use split pairs. We've not used planarity anywhere so far. So everything we've done also works for non-planar graphs. Doesn't have to be a planar biconnected graph, just any biconnected graph. We can decompose this way if we want. But the nice thing is that every skeleton we get is also a minor of the graph. So if we start with a planar graph, then all the skeletons will also be planar. Otherwise, it might be that our rigid structures are non-planar graphs, for example. Also, the other way, if we get a planar embedding of every skeleton and we merge everything together, then we get a planar drawing of the whole graph. So if we start with something planar, then everything we get is planar. And if we make sure that the embeddings are also plane, we get something plane in the end. But you have to be careful that you don't create any crossings there. And like I said, we start with some edge. That's the root. And the root will always lie on the outer face. And whenever we go down the tree, we also always have to make sure that this fake edge, the reference edge we have, that this is embedded on the outer face, because there we have to glue our component into the rest of the graph. If it's not outside, then this does not work. So all the reference edges always have to lie on the outer face if we create embeddings. Otherwise, we just have an embedding on a sphere. Then we can also do the non-rooted version, but I like the rooted version much more. And the key statement is every embedding of G corresponds to embeddings of all the skeletons. And depending on the types of nodes, we can now encode different embedding choices. So for the Q node, it's pretty clear, but if we look at the P node, for example, there are different components. And how we order them, we can choose. That's different types of embeddings. We have linear size, we can compute in linear time. And yeah, here, if we have S nodes, then it's usually very simple. But if we have P and R nodes, then it's usually most challenging. So whenever you have an algorithm that where you want to use SPQR-Trees, you have to look at all these different kind of nodes. You always have to assume that you've solved all those components that are in the subtree, and then you have to figure out how to glue this together. It's usually easy here, but this is usually hard, and this is often the hardest. How can I combine all these solutions that I have for these components to get something for the larger one? And like I said, different embeddings. Here we can choose the order between all those components. Here we can only flip what we have in between. And here we can also only flip all those smaller components. And that's all the different choices that we have to get all the different embeddings. So we can walk through the SPQR tree, and by that we could create all different embeddings that exist, but you have to be careful because there are probably exponentially many. So you don't want to write them all down. Okay. Are there more questions to the definitions? Yes. You can flip while keeping the reference edge. So I can flip this whole part here. Sorry, I didn't. Yes. It depends on your algorithm. So if you want to combine stuff, then you have some solution for whatever your question is. You have solved all these different smaller components, and now you want to solve the graph that you get by gluing all of them together. And there are just many, and they're glued together in some weird ways that makes it tough. So you have to make sure that whatever you want to do still works after gluing stuff together this way. For our problem, they are not that tough. So for us, probably the P nodes are the toughest. But we will see soon. Other questions? Okay, now I've thrown all this theory at you, now we want to use it. We go back to our problem. Remember, the problem was we have a biconnected graph, and we know how to solve the three connected one. So now we want to figure out in this biconnected graph, if I have Mario and Peach, how can I connect them by getting the smallest number of crossings possible. And of course, we now have this data structure, so we start with building it. That we can do with the decomposition in linear time. The next step are very similar to what we've done before. We find Mario and Peach. Let's say they are here. And we find them in the SPQR tree. Okay. Here we have one node with Peach, one with Mario, just to make it simple. Now it's not that obvious that there's a unique path from Mario to Peach, or a unique shortest path. But in the exercise later, you can try to prove that this is true. So you can take this for now, that this exists. So let's take this unique shortest path between a node that contains Mario and a node that contains Peach. And we want to walk along it. And while we want to walk along it, we also want to mark all those components where we're coming from. So this here becomes now orange because we come from Mario. Then we go here. Then we go here. And from Peach, we also walk up to the lowest common ancestor of the two in the SPQR tree. So we go to this component. Then we go up to this component. And then we go here. And now we found the path. And what we now want to do is we want to use this SPQR tree structure to solve our problem. And there's technically two different ways that you can do that. The first one is we can go bottom up from both and meet in the lowest ancestor. And the second one is that we can just walk along this path from one to the other. So going bottom up is basically the rooted version, and walking from one to the other is like the unrooted version where you just walk along the tree. Again, both have their advantages and disadvantages. And then there's also two ways that we construct the whole thing. We can either do it in 2 steps or we can do it in 1. So I will show you, there are basically 4 algorithms. I will show you 2, bottom up, do it in 2 steps, or walk along and do it in 1. So let's have a look at the first strategy, bottom up. We start here in the node of Mario, and we want to walk upwards along the SPQR tree until we reach the lowest common ancestor. We know that we can solve the 3 connected case in linear time. So the first step we want to do is we want to find the best possible embedding for our graph. And in the second step, after we found this embedding, we want to add the edge. And in fact, we will not use the fact that we can solve the 3 connected case, but we will use the fact that we can solve the fixed embedding case, so that we can solve everything that we have in between. Because they might not be 3 connected, but if we say we don't want to change the embedding anymore, then after we fix the embedding for the whole thing, we can just solve it with this algorithm. So the interesting part is step 1. What is the best embedding and how can we find it? And if we want to find the best embedding, then we have to make sure that for every node here in between, whatever represents Mario is as close to the part that represents Peach as possible. So the best embedding means that we walk along here, and every node here has either Mario or Peach, or something that represents it. So here we have Mario and the reference edge that points to Peach. Here we have the orange component that represents Mario, the reference edge represents Peach. So there's always 2 things. And these 2 we want to bring as close together as possible by potentially re-embedding the graph. Let's see. Here we have a rigid component. What can we do at a rigid component to change the embedding? Yeah, we can only flip. So there are 2 choices. And we don't want to use the outer face to connect it because there will be other stuff. So we just look at these 2 different drawings and figure out where is Mario closer to this edge. And it's the left one, so we keep that. We go here. What can we change? it's a P node. Yeah, we can reorder all the components. So we just make sure that this orange component is the leftmost one. And then we re-embed the graph. See, here the order switched. And now in the drawing of the graph, we also have to flip this. We go to an S node. What can we do here? Nothing. We just keep it. We don't do anything. And we go on. Now we're at the least common ancestor, so we have to do the same thing for Peach as well. Here it's very easy because I don't have to do anything. I was lazy. Peach is already at the edge. Here they are already together. Here they are already together. So we come here. The final component, it's a parallel component. We have to bring the orange and the purple together. We can reorder however we want. So let's just make them neighbors. And then we probably have to flip the orange because now Mario is here, Peach is here. We just flip this whole component, and we get this embedding. And now by just walking upwards and bringing the orange and purple always as close together as possible, we found an embedding. And to get the embedding of the whole graph, we can just glue all this stuff together. Or, like we did in this example here, whenever we made a change, I just updated the embedding accordingly. So that now I have an embedded graph. And if I don't change the embedding, then we can use the algorithm that we already have to insert the edge between Mario and Peach into this embedding with a minimum number of crossings. And then we're done, and we find the optimum way. Yes?
Maybe a version of the previous question, but if there are no R components, does that mean that you can always insert plain?
Can you maybe please repeat the question for the stream?
So the question was if there's no R component, whether that means that we can always insert the edge without crossings. It's a good question. I think yes.
If there are no R components, then
Yeah.
we can always keep the reference edge and
Yeah.
component we're in neighbors, right?
It's- So I would say yes, but we can add this to the exercise sheet. The other question? So what I now show this approach. What's the problem with this approach? So what do you not like about it? Okay, it seems like you liked it a lot. So this is basically the approach that I came up with. So it's great that you like it. But the thing I don't like is that it's not clear to me why it's this optimal what we're doing here. We're just somehow fixing the embedding, and in the end we say now we optimally add the edge, but we only added optimally to this embedding that we computed. Why was this good? This is not clear to me from this algorithm. So what's good is that with the separation, it's quite easy to describe and implement. So if I would try to implement this algorithm, I would probably do it this way. First fix the embedding and then add the edge. But it's not so easy to prove that what we're doing here is really correct. So I want to show you a second strategy where these two advantages and disadvantages are flipped. There it's clear that it's optimal, but I wouldn't want to implement it. The strategy is we now want to walk from Mario to Peach. And while walking there, we want to build the embedding and add the edge at the same time. So we always draw some subpath, and those paths we want to glue together on the way. So we don't start with the whole embedding, but we just start with this component here. This is our beginning. And what we want to do is we want to find a path from Mario to Peach. So we already want to use our algorithm for this embedded part here. But there's no Peach here, so we cannot do that. So we first have to subdivide this edge and place Peach on top of it. So we put Peach here. And now we have here it's a 3-connected graph. Now we want to find the optimum way to add the edge from Mario to Peach. The only thing we can change is maybe flip this component. So we again want to embed them such that Mario and Peach are as close as possible. For the R node and S node, that means we can just flip. For the parallel node, that means that we can change the order of the children. But now it's a bit clearer what we mean because there are now really two vertices, and we can better define what is the distance between them. So here it's pretty clear. We add the edge, and we're done for this component. And now we walk to the next one. And what we want to do now that's different is that we have this embedding, and we want to plug it in here. So we want to start building the embedding of the graph on the way. At the moment, we only have this part run. So we take the next component, and we want to draw the pertinent graph of this. So we have some components in here that we don't really care about. This component, we don't care how this is embedded. So we take an arbitrary embedding of this and place it here, like this. But for the orange one, that we have already computed, so we have to add exactly this embedding that we have computed in here and replace the orange component by it. And then we get this component, and to avoid confusion, I replaced Peach by Yoshi here. So we connect Mario to, we still have the connection from Mario to Yoshi from here. And now we add the edge from Yoshi to Peach. We have an embedded graph, so we can use our algorithm to optimally add this edge. And now we've embedded everything that lies here. We go to the next, the parent. There's only one component, that is the component with Mario. We have to add it exactly with this embedding inside here. We split this edge to get Peach. We add this component, and we optimally connect Yoshi to Peach. We get to the next parent. There are again two other components that we don't care about, but first we have to add Peach. Now this is inside a component, but we just do the same. We still subdivide it. So Peach will be here. We change the embedding to bring them together. We replace all these components that we don't care about by arbitrary embeddings. And we place this embedding of this subgraph here where the orange part is. It might be that we have to flip. This is usually once on the way, so here I flipped it from leftwards to rightwards to bring everything together, but that only can happen once. And we have the edge here. That's also not hard to test. You can just try on the way which flip is better, and that doesn't change the running time at all. And now we continue walking. The next one is here. Now this is not really a parent, but this is a child. But since we're just walking along the tree, we can do the same procedure. There's one component where we don't care about. Here we have to put Peach into the component. We're in an S node. We don't have to change any embedding. So just replace this. And now put this whole part here where the reference edge is. So around this. And we get this part. We continue. We put Peach here, bring everything together, replace this component we don't care about, and add this whole embedding into the graph to get this drawing. And finally, the one with Peach. We add exactly this embedding. And now we've embedded the whole graph. And on the way, we've already produced our path from Mario to Peach. And to get the edge, we just throw away Yoshis, let them fall into the abyss, and we have the optimum edge. And like I said, the advantage is that now I think it's much clearer that what we've done is really optimal, because now we can use an inductive proof. On the way, we always have an optimum drawing from Mario to Peach in the current component. And we always just keep on working on it and keep on extending it. But what's much tougher is if we, for example, look at this part here, now we somehow have to glue this here and create the embedding, so it's much more technical. And the description, how do we do all this stuff on the way, you need a lot of notation, you need a lot of indices, so it's much harder to write down. So again, from implementation standpoint, I would probably use the first strategy, go bottom up to the embedding, then at the edge. But if you do the proof, then probably the second one is better. That's also the one that they used in the original paper. And now we're finally done. Assuming that we can do the fixed embedding case, we can also do the bi-connected case. And since we already have the connected and the disconnected, that means that now with this last point in between, we can solve the problem for any planar graph. Are there any questions? Yeah. Yes. The embeddings that we produce in both strategies are the same. I mean it might be, so we have not really precisely defined what we mean when we put them too close together as possible. For example, in a P component, you could just flip it, so there might be two different embeddings that have the same distance. So it could be that you get different ones just by doing different optimal choices. But that's not due to the strategy. Yes. Yes, exactly. So if you use the same rules to determine how to put stuff together, then you also get exactly the same embedding. Okay, I was promised 5 more minutes, so just some final remarks. Sometimes if you do stuff, it might be helpful that you also remove the S nodes and you contract them into the parents. If you get stuck, this might be a strategy that makes sense, because then all the skeletons are bi-connected even without the reference edge, which can make it easier. Because otherwise it's always a bit weird. Sometimes you count the reference edge, sometimes not. And this can make it easier. When the outer phase matters, you have to use the rooted SPQR-tree, then you might have to try every possible edge as the root. Sometimes you can save some time by rerouting along Euler tour of the tree, but usually you would just start with this part first and then later try to optimize. And sometimes the algorithms don't rely on precise definitions of SPQR-trees, but it's usually only important that we want to decompose along split pairs and that we do this for all the nodes. And again, if we look at embeddings, for S nodes, we don't have any choice. P nodes, we have many, many choices, all the arbitrary permutations. R nodes, we can only flip. And Q nodes are such single edges or whatever. And these algorithms, they often also work on other structures that are similar, not exactly SPQR-trees, but where we have decomposition along split pairs. And of course, there's many other problems that use it. Just a small slide from Ignaz with some examples. Deciding if a graph is planar, we can do with SPQR-trees. We can build the SPQR-tree, and then we can try for every skeleton how to embed it in a planar way. And then we saw that will give us a plane embedding in the end. So we can test this. We can test some stuff like we can color vertices, and we want to find some embedding where all the vertices of the same color are in the same face. Or we can maybe extend a plane drawing to something larger that's still plane. Maybe we want to find some special embeddings, like we want to maximize the size of the largest face that we can also do with SPQR-Trees. Or we can do clustering algorithms for that. Or we can do stuff like a simultaneous embedding where we have two planar graphs that we want to draw on the same point set. So whenever you have some structural properties, you want to extend something or you want to glue stuff together, and it's easy for a three-connected case for most of these problems because there's a single embedding, then it makes sense to look at these SPQR trees, try to figure out a way how can we glue stuff together, and maybe you can also solve it for a more interesting bi-connected case. Okay, that's it for the lecture part. Thank you for listening to me for such a long time.